Hi, welcome back to this channel. In this video, we are going to discuss about buffer solution. So we need to know what is the buffer solution, how the buffer solution control the pH value, and then also we are going to determine the pH value of the buffer solution according to the Henderson-Hasselbalch equation. And then we are going to calculate the pH value after a small amount of strong acid and base are added. Let's proceed to tutorial question 11, which is very direct question. Define the buffer solution. So buffer solution is a solution that have the ability to resist the changes in the pH value when a small amount of strong acid or base are added. Remember, it's small amount only. So basically, the buffer solution is made up from weak acid or weak base with the salt which contain its conjugate. So based on the definition above, let's check out, are they buffer solution? Hydrogen fluoride, yes, is weak acid. So if this is the weak acid, the conjugate will be F negative. So in the NaF is the salt which contain the F negative. So this is the first one is the buffer solution. Second, HCl is the strong base, so it cannot be the buffer solution. The third one, H2CO3, it is not in the list of strong acid, so means that we know this is the weak acid. So and then if this is the weak acid, after its conjugate will be HCO3 negative, where we can see it is in the salt. So that's why the third solution is the buffer solution. Fourth solution, NH3 is the weak base. And then the conjugates for NH3 will be NH4 plus. So the salt also contains its conjugate. So this is buffer solution. So the difference between the third solution and the fourth solution is the third solution consists of H2CO3, which is a weak acid. So this one we will know is an acidic buffer solution. While the buffer solution which contains the NH3 ammonia is the base, so we will consider it as basic buffer solution. Next one, CH3COOH, also not in the list of strong acid and strong base, so we know this is the weak acid. So if it is the weak acid, the conjugate is CH3COO negative. So solution, the fifth solution is the buffer solution. Next one, NaOH is in the list of strong base, so it will not be the buffer solution. HCl is in the list of strong acid, so again, this one will not be the buffer solution. Tutorial question 12. A buffer solution prepared by mixing 560 ml 0.2 molar acidic acid CH3COOH. So CH3COOH is not in the list of strong acid, so it is weak acid. So based on the question, it will be supported because the Ka value of CH3COOH is given. And then we have 3.15 gram of sodium ethanoate. So when we look at the formula for the sodium ethanoate, we can see the conjugate base of the CH3COOH. So this can help us to double confirm that the solution is buffer solution. So even if the question didn't mention the buffer solution, so you still have the ability to identify the mixture or the solution is buffer solution. Question A, they ask us to determine the pH of the buffer solution. So like just now we have mentioned, there is two type of buffer solution. One is acidic and then another one is basic buffer solution. So to calculate the pH for the buffer solution, we have another formula which is known as Henderson-Hasselbalch equation. So if the buffer solution is acidic buffer, so we are going to use the formula pH equal to pKa plus log concentration conjugate base over concentration weak acid. While if the buffer solution is the basic buffer solution, then we will get the pOH value. So then the Ka will become Kb, conjugate base will become conjugate acid, the weak base will become the weak base. If we still insist want to determine the pH value for the basic buffer solution, then we have to add on another relationship in your calculation, which is pH plus pOH equal to 14. As this question is mentioned about acetic acid and then Ka is given, so basically we know that we are using the first formula, pH equal to pKa plus log concentration of the conjugate base over concentration of weak acid. In the question here, the question asks us to determine the pH value. However, the Ka value is given, so we can use the negative log Ka to determine the value of pKa. So 0.2 molar is the concentration for the weak acid, also given, but the concentration of conjugate base, which is the sodium ethanoate, is not given. However, they give us the mass, means that from the mass, we can determine the number of mole. Then from the number of mole, we divide with the volume of the solution, we will get the molarity. So basically, this is the calculation way. Mass over molar mass equal to number of mole, and then number of mole divided with the volume. So the concentration of the sodium ethanoate is 0.0686. So then we can substitute this value into this formula. By press the calculator, final answer for the pH value of this acidic buffer solution is 4.28. Before we continue with the tutorial question 12B and C, which involve the calculation, it will be better we can understand qualitatively how the pH value will remain constant when a small amount of strong acid and base are added. Okay, so now this explanation will answer tutorial question 13B. Yes, basically in tutorial question 13B, they are asking us how the buffer solution can control the pH value. So let's take the example based on tutorial question 13B. There is benzoic acid and also sodium benzoate. So in the solution, as we know, benzoic acid is the weak acid. So that's why they are going to ionize partially, while the salt in chapter previous class, we already discussed, salt always will dissolve completely. So we can write two equations as follow. The benzoic acid dissolves partially in water to produce H3O plus and C6H5COO negative. We are going to use irreversible reaction. While for the sodium benzoate, it is a salt which will dissociate completely. Therefore, we are going to use one-way arrow. So because of this, based on these two equations, we know that mainly the species in the container will be the benzoic acid because only partially of them are dissociated. Okay, while C6H5 sodium benzoate, benzoate ion will be the mainly because they dissociate completely, and Na plus also the mainly. Okay, so these are the main species in the acidic buffer solution. However, only these two that we emphasize over here, benzoic acid and benzoate ion, is the main species that will affect the pH value of the buffer solution based on the Henderson-Hasselbalch equation. So if we add in the HCl into the buffer solution, the H plus will going to this H plus is the HCl that we added in, is from the HCl that we added in. So they have two options, either will react with C6H5COOH or C6H5COO negative. So because H plus is partially positive, so they will react with the negative ion to form C6H5COOH. So in this case, when this reaction happens, you will notice that the benzoate ion is going to decreasing while the concentration of C6H5COOH is increasing. So according to this Henderson-Hasselbalch equation, you will notice that the concentration of the conjugate is getting lower, conjugate base, while the concentration of weak acid is going up. So one is going up, one is going down. So you will make that the pH value will remain constant or can be negated. Similar case will happen when a small amount of strong base is added. So as we mentioned just now, benzoic acid dissociate partially, so the main species remain will be the benzoic acid water. While because of the sodium benzoate is dissociate completely, so that's why they will exist in benzoate ion and also Na+. So among these four species, only the benzoic acid and also the benzoate ion will affect the pH value. So when a small amount of OH negative is added, so this time the OH negative will going to react with the benzoic acid to form benzoate ion and also water. Therefore, again, we will notice that concentration acid is decreasing, which is opposite way for the previous condition, while the concentration of benzoate is getting higher. So again, when we relate to the Henderson-Hasselbalch equation, the concentration of weak acid is getting less, while the concentration of conjugate is getting more. So from here, they will adjust it so that the pH value will remain constant. So basically, this is how we explain qualitatively the pH value for the buffer solution can be controlled or remain constant when a small amount of strong acid and strong base are added respectively. Okay, after we have the idea how the buffer solution can control the pH value, so now let's proceed with the tutorial question 12b, which involves calculation. So calculate the pH of the buffer solution after we add 5 ml of 1 molar HCl. So basically, because there will have changes based on the previous slide, we already know the concentration of CH3COOH and also the concentration of CH3CO negative going to have some changes. Therefore, we need to use the ICF table in this calculation. However, the unit that we want to substitute in this ICF table will be in number of mole. Okay, because the concentration will be changes again when something is another species is added on. So first we draw out the ICF table, which in number of mole, initial, change, final. So because of this case, we are adding the HCl into the solution. So we have CH3COOH as the main species and also CH3COO negative as the main species. So HCl will be represented by the symbol of H+. So the H+ from the HCl tend to react with the CH3COO negative and then produce CH3COOH. So from this question now here, we need to find out the number of mole for the CH3CO negative and also CH3COOH. So the amount of the HCl added, we're going to use the formula mv over 1000. So when we use the mv over 1000, we will get the number of mole for the acid added is 0.05 mole, while the concentration, while the number of mole of the buffer solution, we are going to use the formula mv over 1000 as well, and then we get 0.112. Then next, with the mass given for the sodium ethanoate, we divide with the molar mass, so we get the number of mole is 0.0384. So all these are considered as the initial number of mole. Okay, so and then for the changes, you have to remember that HCl is added, so this is considered like a substance that going to react. So the concentration, so all the number of mole of HCl will be completely reacted, so which will minus 0.005, and then due to the ratio is 1:1:1, so for the number of mole of CH3CO negative also will reduce 0.005, and the and the number of mole of CH3COOH will going to increase 0.005. So and then we do some mathematics. So finally, the number of mole of CH3COOH remaining is 0.0334. And then the when we have number of mole, but when we substitute into the pH Henderson-Hasselbalch equation, we need to in form of concentration. So that's why we are going to use number of mole divide with the new volume. How we get this new volume? Because initially the buffer solution is 560 ml. Then we add in 5 ml of HCl. So now the volume of the solution is become 565 ml. Convert to liter is 0.565. So same case happened to the concentration of CH3COOH. We use the number of mole and then divide with the total volume now. So the concentration is 0.207. So then we substitute in these two concentration into the Henderson-Hasselbalch equation. So press the calculator, we will going to get the pH value is equal to 4.2. Question 12C. Calculate the pH of the buffer solution after addition of 3 ml of 2 molar NaOH solution. So again, in the solution here, the CH3COOH and also CH3COO negative are the main species. So when we add in the NaOH solution, the OH negative will going to react either with CH3COOH or CH3COO negative. So because of negative and negative will not react with each other, so the OH negative basically will react with the CH3COOH. So again, before we proceed to the calculation, we know that we are going to use ICF table, and then the unit in the ICF table must be in number of mole. So that's why we're going to convert the number of mole for the NaOH using the formula mv over 1000. Okay, then now we know. Just now we already mentioned the OH negative will going to react with CH3COOH to produce CH3CO negative and also H2O. This 0.06 is we just calculated. And then this 0.112 and 0.0384 basically is from mv over 1000 for the acidic acid, and then 3.15 over the molar mass of sodium ethanoate. Okay, the value we are obtained from the B, so we didn't show the calculation here again. So for the changes, always to keep in mind that all the amount of acid and base added must be completely reacted. So that's why here we are minus 0.006. Due to the ratio of the equation here is 1:1:1:1. So for the for the acidic acid, we are going to minus 0.006, while for the benzoate ion, we are going to plus 0.006. So this is the final number of mole that going to substitute into the Henderson-Hasselbalch equation. However, in that equation, we need to substitute the value of the concentration. Therefore, we need to change the number of mole into the concentration, which will equal to 0.188 molar and 0.0789 molar. So to keep in mind that we are going to use the new volume, which is 560 ml plus the 3 ml of the NaOH. Then again, substitute the value of the concentration into the Henderson-Hasselbalch equation. The pH value will equal to 4.37. Let's continue with another calculation problem which involving the buffer solution. A buffer solution, the pH value is 4.6. How we prepare this? We are going to mix the benzoic acid with the sodium benzoate. So the information of sodium benzoate is not given. However, the information for the benzoic acid is 75 ml with the concentration 0.5 molar. Then next, the question is asked us to determine the mass of sodium benzoate. So now, when we can confirm that the this is the buffer solution. So and the pH value is given. Basically, we will able to use the formula Henderson-Hasselbalch equation. So pH value given, and then in the question here we have Ka value. So there is no problem for us to determine the pKa. So concentration of conjugate base in this case is the sodium benzoate. We have no idea. So this is a question mark. And then concentration for the weak acid, which refer to benzoic acid, we have 0.5. By substitute the value in the question, so we will able to determine the concentration of the conjugate base, which will also equal to the concentration of sodium benzoate, because the sodium benzoate is a monoprotic acid. So if you write the dissociation equation, the ratio is 1:1. So the concentration of sodium benzoate is 1.294 molar. As we know, if we want to determine the mass, normally we need to get the number of mole. But when we have the concentration, we will able to determine the number of mole as well. So in this question, if we have concentration, we want to find number of mole, we are going to use the formula mv/1000. So concentration is here 1.294, but the volume of the sodium benzoate is not given in the question. So that's why we need to do assumption. So you have to mention, assume total volume of benzoic acid and sodium benzoate is 75 ml. Okay, means that because basically we can have the idea that this sodium benzoate basically will be in the powder form. So maybe the volume is quite small compared to the actual one. Okay, so that's why we do the assumption over here, because they didn't give us any information about the volume. So again, once you get the number of mole, like we mentioned, we can multiply the molar mass of the benzoate, sodium benzoate, then we will get the mass should be in the mass of 13.98 gram. Tutorial question number 14. Calculate the ratio of concentration ammonia to ammonium chloride to form a buffer solution with the pH value of 8.3. So basically we know that this buffer solution is basic buffer solution. Okay, because the Kb value is given, so we know that we know the ammonia is the base. So when we also know that this is a buffer solution, we're going to use Henderson-Hasselbalch equation. So because this is the basic buffer, so basically we are going to use POH formula, but the question given us the pH value, so we have to relate the pH value and the POH value always equal to 14. Therefore, we know that POH is equal to 14 minus 8.3, which is equal to 5.7. So then we will write the Henderson-Hasselbalch equation. So we have the POH value. We are able to determine the pKb value. So the log concentration conjugate acid, so in this case is NH4 plus, while for the weak base is NH3. However, the question is asked us to determine the ratio is NH3 to NH4 plus. So means that later after we get the ratio for the NH4 plus over NH3, we need to reverse the fraction. So we consider this one as one unknown. Okay, concentration NH plus over concentration NH3 as one unknown. So substitute the value in, so you will able to get 9.02, which is approximately into the 9. So 9 also will be considered as 9 over 1. So then next, the question again is ammonia to NH4 plus. So that's why we reverse the fraction. So the number also we will reverse. So the ratio is 1 to 9. Okay, basically we already finished for buffer solution and also consider complete for chapter 7.1. So these are the final answer for tutorial question 12, 13, 14, and also the objective answer for question number 1, 2, 3, 4, 5, so 6, 7, 8, 9. So thank you for staying in this video. So hope this video can help you to understand the tutorial question better.